Hi everyone. Thank you for the opportunity to present in this seminar series. So as said, my name is Tengfei Jiang. I'm currently associate professor in the material science engineering department. I'm also affiliated with MPAC, the Advanced Materials Processing Analysis Center. So today I'm going to talk about our work on materials research for interconnect and packaging reliability in advanced microelectronics systems. So first, a little bit of background about myself. I joined UCF in 2015. And before that, I received all my education and training in material science. So overall, my research interests are in the areas of emerging interconnect and packaging systems, reliability metrologies to apply and develop, metrologies to study the reliability phenomenon, and also in fabrication and characterization of materials, microstructure and interface characterization and engineering. I'm also interested in applying advanced techniques such as synchrotron X-ray diffraction to characterize materials. In terms of teaching, since I joined UCF, I've taught 7 different courses, both in the undergrad level and the graduate level. I want to highlight that I taught our capstone senior design course, PMA 4915 and 4916, in its basically inaugural offering for our department, to the first class of undergrad, the graduates from our department. I have also taught among the graduate level courses. Also, 2 of them are our core curriculum. And also here's some highlights of accomplishments. So currently, I am advising 3 PhD students and a few undergrad students. I have graduated 2 PhD students and 1 master's student. So I've worked with my students to publish papers both in peer-reviewed journals and conferences proceedings, including the IEEE ECTC, which is one of the most highly regarded conference in my field. And my students have received many awards, best paper awards, poster awards, travel awards, and so on. And last year, I received the career awards from NSF to support my research and education objectives. So about the motivation of my research, if we look at the trajectory of microelectronics, one thing that becomes really clear is that this is a field that never stops evolving. And traditionally, we have followed the path of Moore's law scaling, where we make transistors smaller to increase device density, to improve the performance. And it has served the industry pretty well until when the landscape starts to change, when we're really stepping into the era of data center, like the previous speaker mentioned. So very demanding on the power and performance, and Internet of Things, and artificial intelligence, and so on. So all of those applications really demands more performance, more miniaturization, more functionality, and at the same time, keep the cost low. So this is really beyond what Moore's law, can take us. Therefore, people have been exploring new technologies, based on new materials, 2D materials, and photonics, and one of the most promising solution is really based on advanced interconnect and packaging, such as 3D integration based heterogeneous integration. So when we do that, we basically have to introduce new materials and new structures, and to enable us to integrate more functions and improve the performance and so on. But there's a potential challenge when we introduce those new materials and structures, and that is due to the interaction and reaction of materials. So you have lots of property mismatch in the material, and that's going to generate stress in your device and causing different failure phenomena to happen, and basically generating reliability issues. So understanding the materials behavior, materials interactions, failure mechanism, and find ways to improve reliability for advanced microelectronics systems is really the main focus of my research. And so achieve that, we take a two-pronged approach, combining both experiments and modeling. And our overall goal is to develop materials processing and to solve reliability problems to enable these new technologies. So I'm going to give 3 examples of the projects in this, under this theme. So the first one is about the reliability of 3D interconnects, in particular copper through silicon vias, which is a key structure to enable 3D heterogeneous integration, and which are really critical for many important applications. So here, this problem again comes from the property mismatch between the copper via and the surrounding substrate. So the thermal expansion coefficient mismatch, will generate a lot of stress in and around the via, and causing deformation and different reliability issues. So this problem has to be understood from a microstructure perspective, and scaling down the via diameter is necessary to allow us to integrate higher densities of vias, but the effect of this scaling on reliability is still not very clear. And also, it's another unresolved question is how do we control the statistics of the via protrusion in these structures? So those are the main knowledge gaps that we're trying to address in this project. And so the objectives are listed here. So we want to establish a quantitative correlation between protrusion, which is the deformation of the via, and the microstructure, and identify critical microstructure features and deformation mechanism that's responsible for the high tail of the protrusion statistics. We want to use modeling to study the effect of scaling on microstructure evolution and then the resulting protrusion statistics, and also develop solutions to control the statistics of the protrusion, and especially based on a interfacial cap layer and controlling the stress. And in terms of the education components of this project, the objective is to promote training and education of students, especially underrepresented minority students in the area of semiconductor science and engineering, to fill a talent gap in the workforce. So here's is an illustration of our approach, again, combining experiments and modeling. So we're going to use modeling to study the scaling effect, microstructure evolution, the resulting stress and deformation. And we're going to combine a range of experimental techniques to study these issues that I've mentioned. And in terms of the outcome of this project, so a minority students has been recruited and is receiving training. Student has carried out studies of annealing and microstructure effects on the statistics of the protrusion. We've had some microstructure characterization done at UF, and we're analyzing the data. And so the student has presented a poster at a workshop that hosted by IMAPS. Ph.D. chapter. I've also given an invited talk at that workshop. And once we finish analyzing the data, we'll prepare journal publications. And in terms of the education part, and I'll talk about this a little bit more later, but right now I'm a faculty liaison for the new Semiconductor Science and Engineering Certificate program. So I'm going to develop a course on interconnect and packaging as part of this efforts, and working with my colleagues on this initiative. So here's another project, and that's focusing on the electron migration in microelectronics. So electron migration is a phenomena where the moving electrons transfer momentum to the metal atoms and causing the migration of atoms. And so over time, this migration of atoms can cause void formation or even breakage of the circuitry. So this is a known problem for interconnects, including the copper lines and solder joints. But one level of interconnect that really hasn't received much attention in the past is the solder joints between the chip and the printed circuit board, which is we call also the ball grid array solder joints. And this is now, the kind of risk landscape is now changing. Actually, it's for a reason related to the previous, what the previous speaker has said, which is, we're going to have a 4x increase, in data center, in the next, 7, 8 years. And, basically there's demands for more power. So as we, increase the power density, the BGA solder joints or these chip to PCB solder joints now is really at a high risk level for electron migration failing. So working with Juniper Networks, we try to address this issue, which really hasn't been looked at before. And so our first challenge is to design and basically build a test system that's capable of supplying a very high current that we need to stress these type of structures. And there isn't any off-the-shelf existing system to do that. So our system basically contains power supplies to supply constant current at a very high current. We're talking about over 72 amps per channel per sample. And the sample is going to be put in a oven for a controlled environment, and then data collections through a computer interface. So with that, we're going to compare different PCB and substrate designs, obtain the EF lifetime, and then characterize microstructure and failure, and with the goal of provide design guidelines for against the electron migration failure. So this is a picture of a system that we built, and this system is capable of supplying over 72 amps per channel, and there are multiple channels in this system. So this is actually really not very easy to achieve. Just give you a reference. So traditionally, when we test electron migration of the C4 solder balls, we're looking at about 1 amp per sample. So this is orders of magnitude higher. So as an outcome of this work, we have concluded one set of testing and using test vehicles specifically built for this project. Another set of testing is close to completion, and we're setting up another set sort of experiment, hoping to launch next week to continue this study. We have just submitted a conference paper on this. Again, I think this is probably the first time someone has actually reported this electron migration reliability of BGA solder joints. Then the next, another project is also address a important challenge in high performance computing, where a lot of power is required for these components. And so the components really increasing in size and the PCBs are getting thicker, and that's really caused the issue coming from the stress and warpage. And so we really need to look at new solder alloys in order to reduce the reliability risk due to stress and warpage. And also, new packaging designs need to be basically developed to address these issues. So, for the new solder materials, we study the effect of different alloying elements on the microstructure, property, and behaviors of these solders. And also, we are going to investigate low temperature solders, which is a new type of material with a low melting temperature. That is of great interest to the industry. In terms of packaging designs, we perform experimental validation, and for finite element analysis, to help with design optimization. And so, in terms of the experimental approach, we make samples, through, some kind of vacuum casting, and, we measure the mechanical properties, also microstructure. And, and here in one study, we looked at two types of tin silver copper alloys with different amount of bismuth added to them. And we also looked at different aging conditions. So with that, we were able to, look at how the bismuth addition affects the intermetallics growth, and also derive the NN parameter that can be used for finite element analysis. And for packaging design, really our experiments provided validation for the modeling, so to really provide guidelines for the design. And this has led to a few papers in the IEEE ECTC conference, and we also have another paper we just submitted this year. So that's those are three projects and highlighting my research. And in terms of future plans, so in research, definitely want to expand these reliability studies to more novel devices and systems, looking for collaborations and hopefully expanding to other systems such as additive manufactured electronics, and also continue to look for federal and industry supports for the research. And teaching of education. So I am involved with the Semiconductor Science Engineering Certificate program, and it's part of that efforts. I'm going to, and also part of the Career Awards efforts, I'm going to develop a new course on material science for microelectronics, metallization, and packaging. And, here's a list of the lab capability. We have a lot of custom reliability testing systems. And also I've been in the past years trying to go through the MRI, grant, try to get a EBSD for our university. I will continue to work on that. So really that's it. And thank you for your attention. And I want to thank my former and current students and also my collaborators and sponsors.